There's a river in Peru that does something water is not supposed to do. Not according to physics, not according to geology. Scientists have known about it for decades. They've measured it, argued about it, published papers on it. And when you read those papers carefully, actually read them, not the headlines, you find the same phrase repeated over and over in the conclusions. Further research is needed. That's scientific language for, we don't know. I want to take you through every explanation that's been proposed for this river. I want to be honest with you about each one, where it holds, where it breaks down, and what's left when you remove everything that doesn't fully fit. The truth is not hidden. Nobody buried it. Nobody classified it. It's sitting right there in open access journals, in university geology departments, in hydrology textbooks. Science, real science, not the TV version, is completely comfortable saying this is strange and we are still working on it. That's not a failure. That's the whole point. The boiling river of the Amazon basin, locally called Shanay-Timpishka, which translates roughly as boiled with the heat of the sun, runs for nearly 6 kilometers through the Peruvian rainforest. It was documented in scientific literature for the first time in 2011 when a geoscientist named Andrés Ruzo visited it as part of his doctoral research. Ruzo had heard about the river as a child from his grandfather. He assumed it was legend. When he finally stood at its edge as a trained scientist, he did what any trained scientist would do. He took out a thermometer. The water temperature at the main channel, 86 degrees Celsius, near the hottest points, 100 degrees, boiling. In the middle of the Amazon jungle, hours from the nearest volcanic activity, in a region where geothermal energy was considered essentially absent, the water was boiling. His first reaction, he later wrote, was not excitement. It was confusion, because the numbers didn't fit. The explanation, the real explanation, the one science eventually landed on, is not what you'd expect. And the path to that explanation breaks down twice before it gets there. The first thing any geologist asks when they see hot water coming out of the ground is, where's the volcano? Geothermal water almost always appears near volcanic systems, Yellowstone, Iceland, New Zealand. The pattern is consistent enough that it functions almost like a rule. Find the hot water, find the volcano nearby. The boiling river is roughly 700 kilometers from the nearest active volcanic arc. In geological terms, that's not nearby. That's an entirely different world. The thermal energy required to heat 6 kilometers of river to boiling point, sustained continuously, is not something that diffuses 700 kilometers through cold rock. So the volcano explanation, the first instinct, the obvious answer, doesn't hold. When the first explanation fails, scientists don't stop. They go back to the data and ask a different question. The second question was, what if the volcano is underground? Not a surface volcano, but a deep magmatic body, a pocket of partially molten rock far beneath the surface. It doesn't express itself as a mountain, but still generates enough heat to warm groundwater moving through fractures in the rock above it. This is a real geological phenomenon. It's called a non-volcanic geothermal system. For about 2 years, this was the leading hypothesis for the boiling river. It was consistent with the temperature data. It explained the geographic isolation from surface volcanoes. Then the isotope analysis came back. When you heat water geothermally through contact with hot rock deep underground, it picks up a specific chemical signature. The ratio of certain hydrogen and oxygen isotopes shifts in a predictable way. It's like a fingerprint. The boiling river's isotope signature didn't match deep geothermal heating. It matched something shallower, something closer to the surface, something that, by all accounts, should not be generating that kind of heat. The scientists had eliminated the two most obvious explanations, surface volcanism and deep geothermal activity. And we're left with a phenomenon that was still very much happening, very much measurable, and very much without a satisfying model. If you like honest science, the kind that doesn't dress up its uncertainty, this is the moment to subscribe. The third hypothesis took a different approach entirely. Instead of asking where the heat comes from, it asked, how does the water get here? The Amazon basin sits on top of one of the most complex groundwater systems on the planet. There are aquifers, underground reservoirs of water, layered at different depths across the entire basin. These aquifers are connected through faults, fractures, and permeable rock layers in ways that hydrologists are still actively mapping. The hypothesis, the water feeding the boiling river, travels a very long path underground. It starts somewhere colder, moves through the subsurface for a significant distance, and passes through rock formations warm enough to raise its temperature gradually over time. Think of it like a slow cooker, not a blowtorch. The water doesn't encounter one massive heat source. It accumulates warmth over kilometers and years. Moving through porous rock the way water moves through a coffee filter, slowly, thoroughly, picking up everything the rock has to give. This model has a name in hydrology, a regional geothermal convection system. The fault system running beneath the area, a structure called the Pachitea Basin Fault Zone, appears to be channeling water upward from deeper, warmer rock layers. The river isn't fed by a single point source of heat. It's fed by a system, a network of fractures that act together like a lens. This model fits most of the data: the temperatures, the isotope signature, the geographic position. Most, not all. There are stretches of the river where the temperature drops unexpectedly, where cold water enters from side channels and the main flow cools by 20 or 30 degrees over a short distance, then warms again downstream. There's something happening at those points, a mixing dynamic, or a secondary heat source that hasn't been mapped yet. Ruzo himself, now running an NGO dedicated to protecting the river, has said publicly that the full picture isn't complete, that the river is still giving up its secrets slowly. How many places like this exist? Not boiling rivers specifically, but anomalies that sit outside our current models, measured and documented, and then quietly filed under further research needed, never making it into the mainstream conversation. The Amazon basin alone is understood at a resolution that would embarrass any geologist if they said it out loud in public. We have satellite data, we have surface surveys, we have models built from incomplete samples across an area roughly the size of the continental United States. The interior is, in large parts, genuinely unmapped at the level of detail that would let us say, here is every place where the rules bend. The boiling river was known to local indigenous communities, the Asháninka people, for generations before Ruzo arrived with a thermometer. It was part of their cosmology, their medicine, their understanding of the land. They called it the river of the shaman. Western science arrived in 2011, took measurements, published papers, and is still working on the explanation that the Asháninka already had a name for. Both frameworks are incomplete, and the combination of both is more powerful than either one alone. Local knowledge as a map, scientific instrumentation as a microscope. There are researchers doing exactly this work right now, ethnographers working alongside hydrologists, geologists interviewing village elders before they deploy sensors. It's slow, it's underfunded, it doesn't produce clean results that make it into mainstream science journalism, but it's producing results. Science is not a destination, it's a process, genuinely ongoing, genuinely uncertain in places. The boiling river isn't a failure of science, it's science working correctly. A phenomenon was identified, hypotheses were generated, data was collected, 2 hypotheses were eliminated, a third was refined. The gap between mostly and entirely is where science lives. We know it's a geothermal system. We know it's fed by a fault network. We know the isotope signature. We don't fully know what's happening at those temperature drop points. We don't have a complete map of the subsurface channel system feeding it. Those are real open questions. They won't make a headline that says scientists baffled. They'll make a paper that says preliminary findings suggest and further sampling required. The pace at which science resolves these edge questions is not determined by intelligence. It's determined almost entirely by funding. The boiling river sits inside a protected natural reserve now, partly because of Ruzo's advocacy work. A site that can be studied continuously over years and decades without the land being cleared or the hydrology disrupted. That's a scientific asset. Continuity. That's what resolves the hard questions. Not a single expedition with a thermometer, not a single paper. There are temperature loggers placed at intervals along the channel, transmitting data continuously. There are water sampling programs running across seasons, dry season, wet season, the transition between them. And heavy rainfall increases the volume of cold surface water entering the system. The main channel cools measurably, but not uniformly. Where the river resists cooling despite increased surface input, that's where the heat source is strongest. That's where the fault channels are most concentrated. This is what active scientific investigation actually looks like from the inside. Not a moment of revelation, a slow triangulation. Each field season, the map of the subsurface gets slightly more detailed. The uncertainty doesn't disappear, it shrinks. The questions don't vanish, they get more specific, which means more answerable. The Asháninka name for the river of the shaman, carries within it a recognition that this place operates by different rules. It is, in some sense, alive in a way ordinary rivers are not. Not alive literally, but responsive, variable, surprising. A system this dynamic, this sensitive to seasonal change, this dependent on a subsurface network we haven't fully mapped. It behaves like something with its own logic. Something that rewards patience and punishes assumptions. If this kind of honest, detailed look at the places where science hits its limits is something you want more of, this is what this channel does. Leave a comment with the anomaly you'd most want to see covered this way. I read everyone. The next topic often comes from there. We don't already know, and that, honestly, is the best possible news. The boiling river is still flowing, still being measured, still giving up its secrets slowly. The way water moves through rock, patient, continuous, indifferent to how long it takes. We'll keep following it.